Welcome to week 3. Week 3 is what I call meat week. Why is it meat week? Because, well, it's the meat of what you're going to learn in the class. It's the glue that holds the class together. It is moving from fundamentals to broader concepts. So this is, you guys will start learning a few more fundamental things just to understand them, but then chapters 5 and 6 will start to tie those things together, and from there on, you'll be learning less new material and learning how what you've learned ties everything in together. So let's move on to chapter 5 and start discussion there. Alright, chapter 5 is all about clouds and precipitation processes, and it gets into some pretty technical material. What you need to understand is that most of what you're going to talk about, or most of what you're going to discuss this week and learn and read, really relates back to a balloon. In this case, so just imagine a balloon full of air. All right. In the case of stability, stability is really nothing but a hot air balloon. Just think about how a hot air balloon works. A hot air balloon goes up because the air inside the balloon is warmer than the air outside the balloon. The balloon will go down when the air inside the balloon is colder than the air outside the balloon. And the balloon will just kind of stay there as long as the gravity pulling it down is the same as the buoyancy forces, the density pulling it upward. As long as those are the same, it would be it would just stay still in the air. Those three situations are the three classes of stability. And stability is one thing you'll learn about this week. Unstable, the hot air balloon is going up. Stable, the hot air balloon is going down. Neutral would be the condition where it's going neither up or down. Normally we don't really talk about neutral conditions in the atmosphere. We usually talk about stable, unstable, or more specifically, conditionally unstable. In those situations where the atmosphere is conditionally unstable, which actually is almost every single day. When the atmosphere is conditionally unstable, it means that something must happen in order to cause the atmosphere to become unstable. And normally that's just something pushing the balloon up. So say for instance, hook that hot air balloon up to a crane, pull it up manually, and once it gets to a certain height, it will rise on its own. That is stability in a nutshell. Now, one thing to keep in mind is lapse rates tie into stability very closely. Lapse rates talk about how fast the temperature cools off with height. Remember, in the troposphere, temperature normally cools off with height. The faster the temperature cools off with height, the more potentially unstable the atmosphere is. And that's where lapse rates and stability really tie together. And that's why those two concepts are talked about together in chapter 5, and you should understand how those two relate to each other. So the lower or the lesser the lapse rate, the less unstable the atmosphere is. The higher the lapse rate, or the greater the magnitude of the lapse rate, the more potentially unstable the atmosphere is, if that condition is met. All right, a very important aside here. Warm air is less dense than cold air. The reason the hot air balloon goes up is because the air inside the balloon, yes, is warmer, but its density is actually what causes it to rise, because it's less dense inside the balloon than it is outside the balloon. If I were to heat this balloon up and make it so much warmer than the air around it, it would rise on its own. The other thing to keep in mind is that if I were to heat this balloon up, its size would increase. That gets important because an atmosphere that is on average warmer, say over the tropical areas of the Earth, that entire atmosphere is less dense, so it's actually more expansive. It's important to know as we go ahead into later in chapter 5 and into chapter 6. Bubble of air. How are we going to make that into a cloud, and how are we going to get precipitation to fall from it? We don't have clouds unless we have condensation. In order to get condensation, we have to make the air reach saturation. This all ties into what we learned last week, and in terms of relative humidity has to increase. How do we increase the relative humidity? Well, the easiest way in the atmosphere is to drop the temperature. One of the ways, the easiest way typically for the atmosphere to do this is by making the air rise. If we raise the air, that cools it off, And remember, lapse rates in the atmosphere, typically the temperature decreases in the atmosphere the higher up we go. So just by raising the parcel of air, or raising that balloon of air, we decrease its temperature, we thereby increase its relative humidity, and we thereby get closer to saturation, and we get condensation. It all ties together. So we raise that parcel to drop its temperature to get the cloud to form. That all ties back into lapse rate. If the lapse rate is higher, it means it cools off quicker in the atmosphere. It means the cloud is easier to form. That's why lapse rate stability ties very closely in with cloud development and precipitation. So that conditional stability ties back into lifting that bubble of air. And if that condition of lifting, that's usually the condition, is getting that parcel to lift, if that's met, then we can actually make the atmosphere unstable. So lapse rate, condensation, stability, and then cloud formation and precipitation, they all tie together. One of the interesting things is if we lift that bubble of air and we get it to condense and form a cloud, that by itself is actually not enough to make it rain. That is not enough to make the precipitation processes happen. So we need something else to actually occur within the cloud, and that's basically the final topic of Chapter 5. Because it's so difficult for rain to develop just because a cloud exists, there's a couple of different processes. There's the warm cloud processes, which is called collision and coalescence. That's basically where you have raindrops hitting one another. That process isn't very efficient, but it can work in very warm clouds. Warm clouds meaning above freezing. The second one is a cold cloud process, meaning that the cloud is at some point, doesn't have to be all below freezing, but is at some point below freezing. That cold cloud process is called collision and it's called the Bergeron process. The Bergeron process basically grows ice crystals at the expense of the liquid water in the cloud. And in those cases, the snowflakes actually grow, and those snowflakes are what fall. Because of the properties of how snowflakes grow, you can actually cause and manipulate the cloud formation. This is called cloud seeding. I've actually done this myself. I was a meteorologist as part of a project. Feel free to read that, my take on that in one of the forums. But beside that, those snowflakes actually grow, and those snowflakes are actually what fall from the sky and actually what turn into rain in summertime thunderstorms. But that's assuming that the surface is above freezing. If the surface is below freezing, the snow can just fall as snow. And then there's those strange situations where the snow would actually fall and melt, and then if the ground is below freezing, it can actually hit as sleet, or in some cases freezing rain. So the precipitation processes are necessary in order for the condensation, that liquid water in the cloud, to actually fall as rain or snow or sleet or hail. Precipitation does not happen just because a cloud is there. Those processes have to happen.